Hello friends. Have you ever tapped search on your phone and wondered why it finds a contact almost instantly, even if you have hundreds of them? Now imagine your phone had 1,000,000 contacts and, instead of searching smartly, it checked every single one from top to bottom. That tiny difference in approach is the difference between a result in a blink and waiting several seconds. And once you scale to the systems that power real apps, poor choices get even more painful. This is not just a theory problem. Every time an engineer writes a loop or picks a data structure, they are making a decision that affects how their code behaves at scale. In this video, we are going to build the intuition you need to think like that engineer, starting with what efficiency actually means. So what does efficiency actually mean for an algorithm? It is not about how fast your computer is, or how long a program takes on one particular run. It is about growth. As the input gets bigger, how do the resources the algorithm needs, whether that is time or memory, grow alongside it? Look at the table on screen. If an algorithm checks every item once, and you give it 10 items, it does 10 steps. Give it 1,000 items, and it does 1,000 steps. Give it 1,000,000, and it does 1,000,000. The count grows in lockstep with the input. A different algorithm might only need 20 steps no matter the size, or it might need 1,000,000 times 1,000,000 steps. That difference in growth behavior is what we measure when we talk about efficiency, and it is exactly what Big O notation was designed to capture. Now that we know we are measuring growth, we need a shared language for it. That is exactly what Big O notation gives us, the capital letter O followed by an expression in parentheses, describing how an algorithm's step count grows relative to the input size n. Crucially, Big O describes the worst case, a ceiling on how bad things can get. If you have a list of 1,000 names, and the one you want is the very last one, a simple scan will take 1,000 steps. Big O captures that upper bound. It also deliberately ignores constants and smaller terms, because what we care about is the dominant behavior at scale. Doubling the speed of your hardware does not change Big O. Picking a fundamentally better algorithm does. The three curves on screen show how dramatically different growth shapes look, and next we will name each one with a concrete example to make them stick. Let's make these classes concrete with a single analogy, finding a book in a library. Big O of 1 means constant time. You know the exact shelf and slot, so you walk straight there. It does not matter if the library holds 100 books or 1,000,000,000. O of log n, logarithmic time, means you can use a smarter search. Imagine the books are sorted. You open to the middle, decide which half your book is in, and repeat. Each step cuts the remaining work in half, so 1,000,000 books only needs about 20 comparisons. O of n, linear time, means scanning every book one by one until you find yours. Double the books and you roughly double the work. And O of n squared, quadratic time, means comparing every book against every other book. For 1,000 books, that is 1,000,000 comparisons. The library analogy stays the same on every slide, so keep these four shapes in mind as we move to real code. Here is the good news. You do not need algebra to spot Big O in code. Look at the left panel. We have a for loop that walks through an array named items once, checking each element. One loop over n items means the work grows linearly, so this is Big O of n, matching our scan every book shape. Now look at the right panel. There is a loop inside a loop, both running over the same array. For every one of the n items in the outer loop, the inner loop runs n more times. That multiplies out to n times n, or n squared total steps, matching our compare every book to every book shape. The structural signal is simple. One loop over n gives you O of n. A loop nested inside another loop over n gives you O of n squared. You can often read the complexity straight from the shape of the code before you run a single line. Alright, let's bring it all together. Efficiency is about how an algorithm's resource needs grow as the input grows, not how it performs on one small run. Big O gives us a shared language for that growth, always describing the worst-case ceiling. We walked through 4 key classes: constant O of 1, logarithmic O of log n, linear O of n, and quadratic O of n squared. And we saw how to read those directly from code structure, no math degree required. The core insight to carry with you is simple. Always choose algorithms by how they scale, not just by how they feel on a small input. These ideas show up in sorting algorithms like merge sort, in binary search, and in nearly every technical interview you will ever take. You now have the foundation to understand all of it. Thanks for watching, and we will see you in the next one.